Okay, I'm Slava Pestov, and today we're going to talk about generics in Swift. So, with other languages that have generics, there are two popular implementation strategies. So one you see a lot is just to monomorphize everything. You take your generic function, and for every instantiation of that function with concrete types, the compiler generates a new specialization. Another common strategy is to use the types to type check the function, but then use some kind of boxed representation at runtime, erasing the generic types. So what does Swift do? Well, Swift does something different, and it will take most of this talk to describe that. But first, let's start by giving an overview of the language. So in Swift, generic parameters are bounded. This means that the type signature of a generic function places constraints on those parameters, which describes what you can do with values of that type. In this respect, it's similar to most other languages that have generics, but different than C++ templates, for example. And bounded generics is what enables us to do separate compilation. So if we can type check and generate the code for a generic function separately from any specific instantiation of that function with concrete types, and we can call it from another module without having the source code available. And what we can do, though, is we can do specialization as an optimization. It's just not part of the language model. And we want to be able to substitute generic type parameters for any type, not just reference types as in Java, for example. And value types in Swift can have any size, and that together with the fact that specialized and unspecialized functions coexist means that we always do the most efficient possible layout for generic types, even in unspecialized generic code. Let's look at a generic function. So this type parameter t, it's unconstrained, so there's not a whole lot I can do with it, but I can pass it around, I can pass it to another function, and I can return it. And I can call this function f with any type. So I'm calling with an integer and a tuple of strings. I can also define generic types. So here we have a simple generic container that stores two values of type t. And different instantiations of generic types, they're different at all levels in the language. So a pair of integers and a pair of doubles, they're distinct in the type system, of course, but they're also different at runtime. So you can reflect the generic arguments, and also they have different layouts. So here I have a pair of booleans, which is 8 bytes in size, and a pair of booleans, which is 2 bytes in size, and a pair of integers, which is 8 bytes in size. And with separate compilation, I can call a function that's defined in another library, and I can pass it in a type that I declare as a substitution. So how does this all work? Well, we're going to look at a simple generic function again, and let's see what it does. So it takes an arbitrary value of type t, it makes a copy of that value, then it moves the copy into the result, and then it destroys the input parameter because it took ownership of it. So in order to separately compile a piece of code like that, we need some kind of abstract runtime representation that allows us to manipulate these values. And this is called a value witness table. So a value witness table, it tells us how to copy, move, and destroy values of an unknown type. It also stores the size and alignment of the type so that we can perform runtime type layout. And this is similar to like the copy and move constructors and destructors in the assignment operator in C++, except in Swift, the compiler always generates these value witness functions for you. So what are some examples of value witness tables? Well, if I have a trivial type like an integer, for example, the move and copy operations just copy the bytes of the underlying storage, and the destroy operation does nothing. On the other hand, with a reference type, copying the reference means incrementing the reference count of the heap memory that the reference points to. Destroying the reference means decrementing the reference count, but moving a reference just copies a pointer without updating the reference count. So let's look at our function again and look at what kind of code it generates. So we're going to use C instead of LLVM IR because it's a little bit less verbose, but still sufficiently low level to convey the concepts that we need. So let's go through that function step by step and see how it maps to the generated code. So first we have this generic type parameter t. And since we're going to separately compile a function and call it with an unknown type t, we have to pass some kind of type metadata at runtime that describes a type. Then we have a return type of t. Since t can have any size at runtime, it has to be returned indirectly through an out parameter. Similarly, the input parameter of type t is also passed indirectly. And note that even though we're using a pointer here, this code still has value semantics and not reference semantics, which means the caller has to give it a pointer to unique memory of type t, and the function consumes that value before returning. Then the local variable is allocated on the stack, and since we don't know the size of type t, we have to allocate the space dynamically, getting the size from the value witness table. Then we initialize the local variable using the copy value witness function with our input parameter. When we return that local variable, we can consume it because we're not going to need it again. So we use the move value witness function to move it into the result buffer. And finally, when we exit the scope of the function, we use the destroy value witness function to destroy our temporary value. OK, so what's this type metadata parameter? And how do you actually call a generic function? What do you pass in? Well, in the simplest case, when you're calling a generic function with concrete non-generic types, you just reference a global symbol directly that describes the type metadata for that type. So, for example, with integers, the compiler will emit the type metadata for that in the standard library, together with a value witness table that tells you how to manipulate integers. With a class like UIView, again, the type metadata is part of the library, and then the value witness table is a standard value witness table for reference types. With a user-defined reference type, the type metadata will be emitted inside your program, but you can reuse that existing value witness table that all reference types share. So here we're going to call our function with an integer and then a user-defined struct. When I call it with an integer, I pass in that integer metadata, and I pass in the integer value indirectly. And then when I call it a user-defined struct, it's almost the same thing, except that metadata is part of my program. OK, but what about generic types? So we already saw how different instantiations of generic types are distinct. So it's no longer sufficient to just emit a single global metadata symbol that describes all pairs of t. Instead, you have to construct the metadata at runtime. So this works by having the compiler emit what we call a metadata pattern for pairs of t. And the metadata pattern describes the layout of a pair abstractly in terms of the type parameter t. And then given the metadata pattern and type metadata for the generic parameters, the runtime can create the instantiated generic type metadata. So for example, the metadata for a pair of ints, we compute the overall size of a pair of ints, and then we also compute the offsets of those fields so we can manipulate the pair of ints component-wise. And here we have a pair of bools and a pair of ints. They have distinct type metadata that was instantiated from the same metadata pattern, and they have different field offsets. OK, so let's look at an example of using a generic type. So here we have a function that projects the second value from a pair. And in the implementation, as before, we have our type metadata for type t, but we have an input parameter of type pair of t. So we have to instantiate the metadata for pair of t so that we can get that field offset. Then we use the value witness function for t to copy that field into the result buffer. And then we use the value witness function for pair of t to destroy the input value because we're consuming it. And let's look at value witness tables for generic types in a little bit more detail. So when we compile the definition of pair of t, we emit these generic copy, move, and destroy operations that they basically delegate to the value witness functions of t. And so when I'm copying a pair, first I copy the first component, and then I copy the second component. And similarly for move and destroy. So if I want to work with a pair of strings, for example, string is a 24-byte type in Swift, so a pair of strings is 48 bytes. And when I copy a pair of strings, I'm going to use the copy function for string once per field. But on the other hand, what happens if I have a pair of booleans? So boolean is a trivial plain old data type, and the runtime knows this. And a pair of t only has fields of type t. So what that means is that a pair of booleans is also a trivial type, 2 bytes in size. So the value witness table that is used for the pair of booleans doesn't call those generic value witness functions. It calls the trivial value witness functions, which are more efficient because they don't have to recurse once for every field of the pair. And in fact, this is the same value witness table that is used for the type metadata for a 16-bit integer, for example. So that kind of wraps up value witness tables and type metadata, and it's important that the reason they're distinct is because there's this many-to-one mapping between type metadata and value witness tables. Okay, and let's look at this example. So this is the same function as before, except it only operates on pairs of integers and not pairs of t. And here, the layout of a pair of ints is fully determined at compile time. We know the field offsets. We don't have to instantiate type metadata. And so it's important that the compiler and the runtime agree on the layout of types. And this is how this optimizer is able to generate specializations. Like here, I wrote it by hand, but in general, the compiler can do it for you when the source is available. Okay, so we've seen generic functions and generic types. What about higher order functions and values of function type? Okay, so here I have a simple higher order function. It takes a value and a closure. It applies the closure to the value, and it returns the result. So how would we compile something like this? Well, as before, it takes the type metadata for t, and then it takes the input and the output indirectly. But what about that closure value? How does that get lowered? Well, closures can capture values from outer scopes, so you have to pass in some kind of context as well as a function pointer. And then this function pointer, as before, it takes an input and an output indirectly because they have a generic parameter type. And to call the closure, I call the function pointer passing in the context. So nothing really incredible going on there. But what happens when I call this with a concrete type? So I'm going to pass in an integer, and then I'm going to call a closure that increments the integer. So this closure, it only operates on concrete types, so it passes the input and the output directly in registers. And it doesn't capture any values, so that we can use null as a context. Well, but the function pointer that we have to pass in takes the inputs and outputs indirectly, so clearly we're missing something here, and we can't just do this. Well, you know, I'm going to throw out a couple of straw man suggestions for how to fix this. So we don't want to treat all function values as if they could be fully generic by passing everything indirectly. And again, we don't want to use any kind of boxing or universal representation for values because we don't want code that only operates on concrete types or specialized code to pay the price for a feature that they're not using. So what's the solution? We call it abstraction patterns. So what are abstraction patterns? And the general idea is that usually in a typical compiled language, you have a one-to-one mapping from the formal type in the source language and the lower type in the compiled code. But with abstraction patterns, instead, our type lowering operation is a one-to-many mapping because you start with a formal type and an abstraction pattern, and that gives you the lower type. And the idea is that you only have to use the same abstraction pattern when a value is used in multiple contexts. And then if you have two values with the same formal type whose lower types disagree, then we transform one into another, and we call that re-abstraction. All right, so let's make this a little bit more concrete. So going back to this example, now we have the terminology to understand what the problem was and what the solution is going to be. So the closure literal since it has a fully concrete type, it has a different abstraction pattern than the function parameter. So even though the function parameter and the closure literal have the same type in the source language, after you substitute the type parameter t, they differ in abstraction, and that's why we have the mismatch. So what we need to do is re-abstract the closure value to match the abstraction pattern of the function parameter, and we do this using a thunk. So this thunk is going to capture the closure, so it needs a context now. So we're going to allocate a context. And then inside the body of the thunk, the first thing we're going to do is pull out the original function pointer from the thunk's context. Then we pull out the original context from the thunk's context. And then right before we invoke the function pointer, we have to turn that indirect result into a direct result by loading it. Then we call the function pointer with the newly loaded direct result. And before we exit from the thunk, we take the direct result returned by the function pointer and we store it back to the indirect result. And now we call our function apply with a thunk instead of the original closure, and everything should work out. Okay, so there's a lot more we could say about abstraction patterns, but unconstrained generics are kind of boring. There's just not a lot you can do with them. So I'm just going to end it here, and my colleague John McCall will tell you more about constrained generics.
Right. So Swift has a very powerful generic system, a very powerful system of constrained generics, and those are expressed by what we call protocols. Protocols are a lot like what you would see, features that you see in other languages with first-class generic features, such as signatures in StandardML or type classes in Haskell. A protocol is basically a set of requirements. The simplest sort of requirement that you have, for example, in this equatable protocol, is just a function requirement, which says that every type that implements the equatable protocol has to provide an equal operator. The dual notion to a protocol declaration is what we call a protocol conformance, which is where you simply say that, which is how you define how a particular type conforms to a particular protocol. For example, the person type that I'm defining here implements the equatable protocol, and in order to do that, it has to satisfy all the requirements, and it satisfies the requirement in this case by providing exactly that equal operator. So what are all the different things that we can express in a protocol? Well, we've seen function requirements. The next one I want to talk about is that sometimes when you have a function requirement like this, it needs to be defined in terms of some type other than just the type that conforms to the protocol. For example, if I want to have an iterator protocol that I can use on types that can be used to iterate over collections, I want to give it this next method that I can use to pull out the elements of the collection one by one. But it has to return some sort of type. And in order to do that, and the type that it returns is going to be specific to the collection. So that's what we call an associated type requirement, in which you simply declare the associated type like this, and now you can use that type within the requirement signatures within the protocol. Well, here, for iterator, I don't really need to impose any additional requirements on the element types of my collection. But when I'm talking about something like a sequence, which provides a method a method for getting the iterator that I can use to iterate over it, that iterator is itself another type. And I need that type to implement the iterator protocol. And that's what we call an associated conformance requirement. Now, once you have these sort of associated types and associated conformance requirements, you end up with a sort of tree of associated types. And oftentimes, you want to establish relationships between those associated types. And that's what we call a same type requirement. So, for example, sequence has an iterator type, and the iterator type has an element type. But I also want to be able to talk about the element type of the sequence itself. And so I can declare this element type here just like this. But if I declare the protocol like this, these two types could be completely independent. Like the iterator doesn't say, there's nothing here saying that the iterator has to return elements of the same type as the sequence. So I have to define that by providing this sort of type equality constraint. And that's really interesting in terms of the complexity of the protocol system, because it all of a sudden creates multiple redundant ways to identify the same type in a generic context. The final bit of complexity that I want to talk about here is that these sort of associated protocol constraints, these associated conformance requirements, can actually be recursive. So, for example, if I have a collection protocol, this is going to refine that sequence protocol that I just talked about. Well, the primary thing that you want to do with a collection is you want to be able to index into it with a subscript operator. But I also would like to be able to slice into it and get, given two indices and produce a new collection. So for that, I'm going to provide another subscript operator that returns an associated type, a subsequence associated type. Okay. And examples of this would be strings and substrings, or arrays and array slices. But again, this subsequence type can't be completely unconstrained. I really want this to be a collection, and it has to be specifically a collection whose element type is the same as the element type of the outer collection. Now, there's an interesting thing about this. Subsequence, of course, is a collection. And so it has all the associated types of a collection. It has an iterator type, it has an element type, but it also has a subsequence type. So as stated right here, I actually have an infinite tower of associated types in my protocol. I can keep drilling down to subsequences. Now, for something like string and substring, or array and array slice, that's not very useful. I'd actually like to know that when I slice into a slice, I just get a slice back. And so I can do that again by establishing a type equality constraint, and it sort of ties off and gives me back a finite set of, a finite family of associated types for this particular protocol. All right, so that was a quick overview of what you can express in the protocol system in Swift. So let's get into the meat here about how we actually compile constrained generics. So here's a simple little example. It's a function that takes two different collections potentially of different collection types, but they have to have the same element type, and moreover, that element type has to be equatable. And the only thing that this function is going to do is check whether the first element of each of these collections happens to be equal. So when I'm talking about this sort of generic signature, there's really three important things I need to know. I need to know whether two particular generic types, unknown types, are different or whether they're the same. That's going to be vitally important for type checking. I also need to know what protocols, what things that I actually know about an arbitrary unknown type that's expressible in this generic context. And finally, for compilation, it's going to be really important that I know why I know these things. So let's apply that to our example. What are the unknown types in this context? Well, it takes two generic type parameters, C and D. And C and D themselves have associated types. We don't know anything else about the iterator type and the slice type of these two associated types of C and D, right? They're completely unconstrained. So those are all the independent associated types. But they also all have an element associated type. And that's the same type for every single one of these unknown types. So in this generic context, I end up having exactly 7 associated types, 7 unknown types. So what do I know about the associated types in this context? Well, I know that C and D are collections, and then from the fact that the C and D are collections, I know what protocols they variously implement. And then I also have top-level information about C.element. So it's important that for any of these unknown types, I can actually recover Y. And that's what we call a requirement path. So if I take one of these requirements at random, I can produce a requirement path for why I know this information. And a requirement path is simply a path of information starting at some sort of top-level requirement of the generic context and proceeding along a path of specific information that I know from one particular protocol. So for example, I know that C is a collection because that was a top-level requirement of this function. But I know that C.iterator implements the iterator protocol because C is a collection, and therefore C is a sequence, and therefore, because from the sequence protocol, that C has an iterator-associated type, and that iterator-associated type conforms to the iterator protocol. So once I've type-checked this generic context, I end up with this set of a canonicalized signature, which is basically just the set of primary type parameters, and then a minimized set of the top-level requirements, as you can see here. And from that, I can answer those three vital questions. I can, for any particular arbitrary associated type path, I can canonicalize it down to a single element, to a single canonical path that tells me a single canonical path. And that allows me to figure out whether two types in this generic context are the same type. Once I have one of these unknown paths, I can map it to a set of requirements, a set of protocols that I know that unknown type implements. So for example, here, I know that is the same as C.element, and therefore that it just implements the equatable protocol. And when I'm talking about a pair of an unknown type and an associated and one of these requirements on it from the previous step, I can produce one of these requirement paths. For example, I know that subsequence.iterator implements the iterator protocol because of this fairly long, complicated path. All right. Now that we have all that, we can get down to the meat of how we actually compile and type check a generic function. So let's go back to that example. What are the top-level types here? Sorry. How do we lower the signature of this function? Well, we've already talked about this before, a lot of this before from the section about unconstrained generics. So it's going to take C and D indirectly, because those are unknown types. But the result type bool is a known fixed type, and so we can just return that directly. We also have to take the type metadata for C and D as direct parameters. And finally, we have to take in the information somehow about these top-level requirements, that C and D are collections and that C.element is equatable. So how do we pass that in? The answer is what we call a protocol witness table. And much like type metadata is the runtime representation of a type in the type system, protocol witness table is the runtime representation of a protocol conformance. And it's constructed in very much the same sorts of ways as type metadata are. It's generated when you compile the protocol conformance and possibly needs some sort of access function if it's a generic conformance itself. What does a protocol witness table look like? Well, it's going to be based on the structure of the protocol. When we have a protocol like this, much like we took that generic function, we broke it down into sort of this core canonicalized signature, we can take this collection protocol and break it down into a sort of core canonicalized signature. What are the new types, the new associated types introduced by this protocol? And what are the canonicalized, minimized set of requirements upon those new types, the new things introduced by this protocol? And then finally, which expressed in terms of all of that, what are the function requirements of this protocol? Once we have this, we can basically go through it one by one to generate the protocol witness table, which kind of looks a lot like a vtable that you might be used to from C++. So the first thing is this associated type requirement. Now, associated types, like we mentioned, they can be an infinite family in the most general case. And we don't want to have to eagerly instantiate type metadata when we're getting a protocol witness table like this. And that means we don't want to store the type metadata directly in the protocol witness table. Instead, what we're going to do is we're going to turn this into an access function, a function pointer that's stored in the conformance that we can call in order to get the type metadata back. So the next requirement here that we see is the sort of base requirement that we know from the fact that collection extends the sequence protocol. Now, unlike some of these other cases, this can never actually be an infinite cycle. This sort of derivation is always bottoms out in a finite way, because otherwise it would be impossible to declare a conformance to the type. So this, we can actually just go ahead and store the protocol witness table for the base protocol directly in the protocol witness for the derived protocol. But when we go back to the more general case of associated conformances, again, this could be an infinite hierarchy, and we also don't want to have to eagerly instantiate this. So much like we did with the associated type metadata, we're going to store the associated conformance metadata, the associated conformances protocol witness table. We're going to access it using an accessor function, a function pointer that we store in the protocol witness table. And for both of these cases, we pass the witness table for the collection into here so that we can use it to cache this information if we need to. The next set of requirements in here are these type equality constraints. But the type equality constraints aren't really needed at runtime. They're very important for the type checker, but for the overall system at runtime, that's just information that we assume. So these just completely disappear in the protocol witness table. And finally, all of these function requirements just turn into function pointers, just like an ordinary vtable. And that's it. That's how we generate a protocol witness table. So going back to our example of, so how do we pass in these various information, the fact that C is a collection? Well, we pass in the protocol witness table for collection. And similarly, we pass in the fact that C.element is equatable by passing in the protocol witness table for equatable, corresponding to that particular conformance. All right, so now we have the function signature further expanded. So what does the function body look like? Well, the first thing that we're going to need to do in this function, just going left to right in ordinary evaluation order, is that we're going to have to call C.startIndex. So how is this compiled? Well, the real place where we should start is, why do we know that C even has a start index member? And the answer is, because we know that C is a collection. That's a basic requirement of collection. And so we have a requirement path starting at at something that we know at the top level in our generic function. And so in order to actually call C.startIndex, we just have to follow that path, which is easy because we actually have that directly as an argument to our function. So we can just go ahead, load that function pointer out, and call it. Well, so the next thing that we want to do in here is we want to call the subscript operator. Again, why do we know that the subscript operator exists? Well, because it's a requirement of collection. And here's the requirement path for that. But there's something interesting about this requirement. It returns C.element. And we don't know anything about C.element right now in this function. We don't have any information for that. And because it's a value of that type is being returned to us, we need to have, it's going to be returned to us indirectly, which means we need to allocate space for it. In order to allocate space for it, we have to get its size. In order to get its size, we have to get its type metadata. But we don't have its type metadata. So how do we get that? Well, again, you can sort of go back, it all comes back to requirement paths. Why do we even know that C.element exists? Well, the answer is because it's a requirement of the sequence protocol that we know that C conforms to. And there's a requirement path starting at a top-level requirement in our context. All right, so in order to get the type metadata for that, we just have to follow that requirement path. And that means going from C as collection down to C as sequence. And from that, we can call the associated type accessor to get the element type for c.element. And once we have that, we can actually use the size from that in order to allocate an object of the element type. And now, finally, we can go back to the subscript operator and just pull it out of our collection protocol witness table and call it. Well, that was a lot of work. It's a lot of code. How far have we gotten in this function? OK, so we've got the left-hand side of the equality operator. So as you can see, this is a lot of code. We've called like 3 different functions. We've done a ton of loads. A lot of them are dependent loads. We've allocated memory on our stack. This is not efficient code. But it doesn't really need to be. We weren't expecting this to be as efficient as specialized code. The important thing is that this code is basically doing the same things that we would want to do in specialized code, which means that it transparently interoperates with specialized code if part of this needed to be specialized. And that's really the core requirement, the core design goal that we wanted all along, that we can compile and specialize generic code into specialized code that works exactly the same way so that we don't have to impose any basic performance limitations on specialized code. And I'm probably over time, so thank you very much.
OK, we have some time for questions.
Oh, great.
Hello. Would the value witness table be the right place to optimize things like a pair of bools could fit into a bit field instead of 2 bytes? Like where would stuff like that go?
Generally, what we would do there is, that's really sort of a question about storing. The value witness table is sort of representing the canonical, most general abstraction of the type. So like Slava talked about abstraction patterns, there's a most general abstraction pattern that you use in sort of fallback cases where you don't have a more specific information about it. And the value witness table is always encoding that sort of most general abstraction. If you have more specific information about the fact that, a pair of bools is a bit field, when you're storing a pair of bools in its most abstract form, we really don't want to have to do bit field abstraction code in order to access the things. So in its most general form, of course, a pair of bools, it's going to be represented as a 2-byte chunk of memory. If you concretely know that you have a pair of bools, and that's embedded in some sort of larger structure, then the layout of that larger structure can sort of break that down. There's nothing about our compilation model which requires us to actually expose that thing as being independently addressable. We can always create temporary memory, store that thing into that, load it out from a bit field, put it in temporary memory as a struct of 2 bytes, and then pass that off, do whatever operations we want to do on it, and then write that back. And that's a very core element of our memory model, our ownership model, that we've tried very hard to preserve, precisely so that we can do that kind of layout optimization. We don't do it right now, but it's something we want to do in the future.
Is value actually distinct from the protocol system, or is it actually a protocol that is just known to the compiler?
Sorry, what?
So you have your value witness tables and you have your protocol witness tables, and it seems like value
we don't treat value as a sort of core, as a sort of protocol. It's okay. Basically its own concept. There's a lot of additional, everything that we said, all like the actual structs, they're lies. So, this is not ABI documentation. There's some additional structure, additional flags, things like that we store in there. That's very much specific to the task of representing a value. Okay. And if we had one of the things that we are planning on doing is introducing the idea of non-copyable values. What we would do there is we would simply not provide those value witnesses. We wouldn't have a different concept of a value witness table.
Okay.
Yeah.
This is very cool, but what is design? what is the rationale behind the design to go with this model as opposed to C++ with concepts or Rust? Just like in a short form.
Yeah, I think the core thing is that we wanted to allow generic code to be run, like as generic code, and there's a variety of reasons for that. Sometimes one reason for that is that sometimes it could actually be the fastest way of compiling it. Like probably not for running it, probably not for most of these cases, but like you could imagine like if you had some generic code that was mostly, it was generic, but it wasn't manipulating the generic values all that often, or if it didn't need to actually copy them or anything like that, it could actually access them in place. For example, if you were just calling a function on all of the members of a collection, and you were able to call that function on the members of the collection in place, right? Then that isn't actually an operation that necessarily benefits from being specialized in any way, unless you're actually going to specialize it all the way down to devirtualizing the function itself, right? So there is a potential for for generic code actually being the optimal way of representing things. And then that also allows some interesting things down the road that we're thinking about in terms of things that are generic not over types but over values. So for example, we could unify the concept of a dynamically sized matrix with a statically sized matrix in a way that a lot of languages do, frankly, a very poor job of. Because often, the type system itself forces a dichotomy there, forces a split between those two things, and you have to shuffle back and forth in fairly awkward ways. Whereas Swift could potentially just treat that as a sort of runtime, as a runtime property where we stored the size as part of the type, and so it would just be an element of the layout. But the bigger thing, I think, But I think, the bigger thing is that we really want to allow completely separate compilation. We want to allow generic libraries that don't have to describe exactly, they don't have to publish the way that C++ templates do. They don't have to publish their implementation as part of their core interface, right? You can reserve that behind the scenes and then just sort of provide specializations for specific types that you expect to be called at, if that's a very important thing that you want to do.
Even for non-generic types, we also have a mechanism to manipulate them opaquely so that you can separately compile a library that exports some value types and then use it in another program and change the library to add fields or remove fields to the value type. So it's a bit more than just generics.
Right, and that ends up requiring a lot of the same mechanics behind the scenes.
Yeah.
You still need witness tables, you still need dynamic allocation and stuff you need.
Yeah, I heard someone in the audience say separate compilation, and that's exactly what it's about.
Well, we're going to have modules so, in C++ soon. So.
I didn't get one detail. So when you mentioned specialization as a way of optimization, do you require users to specialize, say, functions for with some types, or can you statically determine that it's going to be profitable and generate a specialized piece of code for some types?
We can do both. So you can export specializations from a module for a fixed set of types. This functionality it's implemented. It's not really complete, but it's there. Then the other thing you can do is you can export the body of a function as serialized IR, and then the client will specialize it or inline it as it sees fit. And within a module, all the optimization and inlining and specialization kind of happens automatically. You don't really have to think about it. Like the optimizer will generate whatever specializations it needs. And across modules, the developer has to think about, okay, like which functions are part of my ABI and which ones I can make completely transparent to the client for optimizations.
Thanks.
All right, let's once again thank the speakers, Slava and John.